In the last lecture, we had looked at, last couple of lectures, we had looked at PN junction. And our interest in PN junction was for two reasons. One is PN junction, as I said, is an important device by itself. It's used in various applications as rectifiers. I showed you as light emitting diodes, solar cells. It has many applications. The other reason why we need to understand PN junction is it's an integral part of bipolar junction transistor. And without understanding PN junction, you can't understand bipolar junction transistor. Similarly, PN junction is also an important part of a MOSFET here. All right, so let's begin our discussion related to bipolar junction transistor. And I have mentioned earlier the people who are credited with the discovery of bipolar transistors. And I had suggested that go and look at this particular link. You have the history of invention of transistors described very nicely in these YouTube videos. So I'll pass it on to you. All right, so let's start. The first thing is, what is when I call a three-terminal device as a transistor, what do I really mean? Okay, so in effect, what is a transistor? Action. When can I call a three-terminal device as a transistor? And once we understand that, then we need to understand how does it occur in a bipolar junction transistor. So henceforth, bipolar junction transistor I will simply call a BJT. Now, you will see that BJT, bipolar junction transistor, is called bipolar junction because there are two PN junction diodes. So one of the issues is bipolar junction transistor simply two back-to-back diodes connected together? That's another question to keep in mind. And the third one is, towards the end, we'll see how does a BJT amplify? How does the transistor action lead to amplification here? All right. So let's look at this picture here. Transistor can be thought of as made of these two words here, trans and resistor. And these central characteristics of a transistor is that the current, so there is an input side here and there is an output side here. So it's a two-port device here. Input port is here and an output port is here. And one of the central characteristics of a transistor is that the output current that you see here, I0, is much more sensitive to the input voltage, Vin, and much more sensitive to Vin as compared to its sensitivity to V0. This is one of the central characteristics of a transistor. I0 is sensitive to Vin and is insensitive to V0 here. And so that's the central feature you have to keep in mind. Okay? All right. So ideal in quotes, what would be an ideal transistor? Well, let's see. It may look something like this here. Ideal transistor. Why? Well, we note that if I look at the output current doesn't depend on V0 at all. So we said a transistor would be an element where output current is very sensitive to input voltage and not sensitive to V0 at all. So here I've drawn a equivalent circuit and we find I0 doesn't depend on V0 at all. In that sense, I'm calling it an ideal transistor. And it depends on Vin. And we call this parameter GMVI. So from the output side, we see that this is what we are looking for. An output current which doesn't depend on V0 and an output current which is sensitive to Vi here. From the input side, we find it's an open circuit. Why? Because we'll see transistors we want to amplify. And, if it's an open circuit, it means it does not draw any current. Right? It does not draw any current from the source. So that's a good feature to have. Whatever source you connect, it doesn't draw much power from that particular source here. Okay? Now, obviously, this is a hypothetical element. You cannot have such an element. We'll see a little later on. You can see it here also. If for example, it would violate the conservation of energy. For example, I could connect a source here, right? And I could connect a load here. If I connect a source here and I connect a load here, you'll see that it doesn't draw any power, obviously, from the source because it's an open circuit here. And there is a current here, it flows into the load, and therefore I have power. I have power dissipated in my load here, and then where is that power coming from? So obviously, it's not a complete picture. It's an idealized element. You won't find it in practice. Okay? So, but to keep, what it illustrates is, this is what we are looking for. Okay? These are the kind of characteristics that we are looking for. Central feature is I naught independence of V naught and I naught dependent on Vi. The same thing, I can represent it in the form of a graph. I naught dependent on Vi, I can draw by a straight line like this here. I naught versus Vi goes as a straight line. And I naught independent of V naught, it means that if I plot I naught versus V naught here, then I will see a series of flat lines like this here. So this is current at Vi1, this is current at Vi2, this is current at Vi3, and note it's independent of V0. Okay, so this is what we call as the output characteristics of a transistor. The variation of I naught with respect to V naught for different values of Vi1 is called the output characteristics, because we are talking about output current and output voltage here. This is what we call as transfer characteristics. Output current versus input voltage here. So we call that as a transfer characteristics, and we call this as a output characteristics. So if you're looking at a circuit, then this is what you're looking for in a transistor. If you're looking at a graph, then you're looking for something of this kind here. I naught versus V naught of this kind, I naught versus Vi of this kind. That's what you're looking for from a transistor. Okay? And in effect, this is nothing but a voltage control current source. Okay? So these are the things that we are looking for. Now let me just illustrate quickly that if I have an element like this, I can amplify. Okay? So here is so as I said, I've taken a source here, connected Vs that I want to amplify, and I've connected a load RL. And then we said our ideal transistor looks like this here, voltage control current source here. So I put the circuit together, and very easy to see that the voltage gain V0 will be nothing but GMVI times RL with a negative sign, and Vi is nothing but Vs. So the voltage gain, output voltage versus input voltage, is minus GMRL, and it's easy to see that whatever GM I have been given, I can always find an RL such that GMRL becomes larger than 1, and therefore I can amplify. So you can clearly see that if I had a device like this kind, then if simply by connecting RL and a source, I can easily amplify. Okay? But keep in mind, amplification is not simply voltage amplification. I can call something an amplifier if there is a power gain. Then only I can call an amplifier. All of you are familiar, if you take a transformer, I can feed in a small voltage, transformer can step it up, right? But I don't call it an amplifier. Why? Because there's no power gain. So to call something an amplifier, you have to have a power gain. Okay? Which means that the output power that you get here divided by input power must be greater than 1, which is obvious in this particular case. Okay? And so here I'm talking about a voltage amplifier, and I've said the condition for voltage amplifier, I mean, if you have a situation like this, a transistor like this, it's very easy to get a voltage amplifier here. Okay? But keep in mind, for a 3-terminal device to be called an amplifier, in general, you have to have power gain. Without power gain, you don't have an amplifier. Okay? Alright, so let's come back to bipolar junction transistor. I've shown here a bipolar junction transistor schematic, simplified schematic of a bipolar junction transistor. We have an NPN transistor here. It's a 3-layer device that you see here in the simplified form, N here, P here, and N. And that's the symbol of the transistor that you see here. Base over here, collector here, and emitter here. And the device gets its name, the terminal gets its name, emitter and collector, mainly because when we bias it, normally what happens is electrons are emitted or injected from the N-type, and then they are collected at this side here. So that's why it gets the name emitter. It injects electrons, and this one collects the electron here. All right, so the emitter and collector come from that terminology here. And so the arrow, of course, here that you see, arrow denotes because if the electrons are going from emitter to collector here, then the current, as you can see here, comes out of the emitter terminal here, because the current is opposite to the flow of electrons, so the current is coming out here. All right. And also another way of looking at it is there's a PN junction here. So if I look at the arrow of the PN junction, the arrow points into the emitter side here. Okay, so from P to N. So that's an NPN transistor. A complementary part of that is a PNP. emitter is made p-type, base is n-type, collector is also p-type here. The arrows, the symbols are over here. Okay, so these are the two transistors. If we understand NPN, obviously we'll understand PNP. The roles of electrons and holes are simply reversed. And the other one is that the direction of currents are reversed. In this case, as you can see here, the emitter current normally comes out here. In this case, the emitter current goes here. So the current is flowing from emitter to collector, and here the current is flowing from collector to emitter here, because of the difference between electrons carrying current or the holes carrying current. Okay. All right. So while you look at it, this is the simplified schematic that we draw here, but this is not how a bipolar junction transistor really looks like. A better picture of a bipolar junction transistor is over here. Now, what we have is a silicon wafer or a silicon crystal, which I'm assuming initially is p-type. And this is where your bipolar transistor is. All this region that you see here. This is the bipolar transistor. You can see here, there is an N plus region here, which is the emitter. Then there is the base region here, p-type, which and the contact to the base is over here. And then there is an N-type region here. This is the collector. The contact is here. All the contacts that you see here in a bipolar transistor normally are all made at the top. This is a planar bipolar junction transistor. Emitter is here, base is here, and collector is here. Okay, so that's where the contacts are. Also note some other points about this transistor here. The emitter is heavily doped, and that's why we denote it by writing plus here, N plus. Heavy doping. Look at the doping here. It's just a typical value. Doping can be larger or smaller. Typically, it can be larger than this. 10 to the power 19 per centimeter cube. So it's a heavily doped region here. Its thickness, note, thickness is pretty thin, maybe 1000 angstrom. As I said, these are typical values. It could be 2000 angstrom, it could be less. So 1000 angstrom, just to give you an idea of the order of magnitude. So emitter is heavily doped and thin. Base that you see here, all this P region here, base, say a doping of 10 to the power 17. We also try to keep this base thickness that you see here as thin as possible. The transistor speed and current gain and all that depend on the base thickness here. And so that's the base here, 10 to the power 17. The collector is over here. All this region is collector. And collector is lightly doped, 10 to the power 16. Could be higher also, could be 10 to the power 5 times 10 to the power 16, could be 10 to the power 17 as well. These things vary. Could be even lower doping. Alright, so that's the collector here. And so this is how a bipolar transistor actually looks. And typically what would happen is, as I said, you start off with a p-type silicon wafer, and then you successively add impurities, n-type and p-type and n plus and all that, and then you make the transistor on the silicon wafer here. One after another, you add different kinds of impurities and in selective regions, and you make the transistor here. This N plus region that you see here, that has been made because if you realize the electrons start from emitter, go to the base and come to the collector. But eventually, where do they have to go? They have to go all the way here. And in order to minimize the resistance, what has been done is a N plus layer has been created here. Because note, the vertical dimensions that you see here are in thousands of angstrom, while the lateral dimensions is in microns. Could be 1 micron, could be 10 micron. Okay, so it's not drawn to scale. The lateral dimensions are, as I've shown here, the emitter length itself could be 1 micron. So laterally is pretty large, vertically is thin. And that's why N plus region has been added. So once the electrons come here, they go to the N plus here, and then they travel along the N plus layer laterally, and then they go to the collector here. So it's all done to minimize some series resistance, collector resistance of the transistor here. Okay, so that's the picture of a better description of a better cross section of a bipolar junction transistor. Note all the contacts are at the top, emitter, base, and collector. Also note that even though both emitter and collector are N-type, transistor is not a symmetrical device. Emitter, you can see here, is N plus, and collector is also N, but look at the difference in the doping. 10 to the power 16 here and 10 to the power 19 here. So you cannot simply interchange emitter and collector and hope that the transistor would behave the same. Emitter is different from collector, even though both are N. Okay? So it's not a symmetrical device. Alright. Now the transistor that we draw If we go back and look at the transistor that we draw, where do we get that? So most of the action, the transistor action that I talked about, it occurs here. This is the place where electrons are injected. They go to the base here, they recombine with the holes here, and then they come here. So this is the heart of the transistor. The other things are like support structures. To provide a contact here, I need this region here. To provide a contact at the top, I need this region here. The real transistor is over here, the portion which is shown between the dotted lines here. That's the real transistor. The rest of it are simply, spaces to provide contact. Okay, so that's the transistor here. And in this transistor, we'll see the role of P minus is, you seldom make one transistor on a wafer. You make several transistors. So P minus, the role is to isolate one transistor from the next. We'll see that later on. So, and N plus is simply there to provide a contact, a good contact to the collector here. So many times what happens is P minus we ignore, N plus also we ignore, and we draw like this here. We draw a transistor by saying there's a contact here and there's a contact here, and then we make a contact here. Note, there's no contact to the side. You don't contact the base here, the base is contacted here. All right, somewhere over here. And you don't contact the collector right at the bottom. You contact again at the top, but through this, all these elements that you see here. But in a simplified form, we denote like this here. Emitter here, collector here, and a base here. Okay, so when I draw a simplified schematic like this, please keep in mind this is simplified schematic. What is real is somewhere here. Okay, but again, when I draw like this, a base here, all I'm saying is that there is a contact to the base, and you can see here, the contact is, it's on the side of the base, as you can see here. Okay, if this is a base here, this exists on the side here. All right, so in that sense, understand where what this contact really means here. Okay, this is the top view. Till now, what I was drawing was a cross section, and the top view looks like this here. There is a region emitter here in the center, then there's a region base here, then there's a region collector here, and we make contacts to the emitter, we make contact to the base, and we make contact to the collector. This is again a simplified schematic, and the contacts are made, and then you make a big metal pad here, and as I said in an earlier lecture, you attach wires, and these wires eventually go to the pin of your sample, the container or the sample holder. Okay, so it goes there. All right, the package. So this goes to the pins of the package here. So that's how a transistor from the top looks like. All right, so that's the background. Let's look at how the transistor operates. Okay, so we look at an NPN transistor, and you see an N region and a P region here. I've not indicated, but remember. Okay, so and I have forward biased the PN junction. I've applied a negative voltage to the N type, and P type is ground. So it's forward biased, and when you forward bias it, you realize that the electrons get injected from N to P region, and the holes are injected from P to N. That's what will happen here. So the total current which is flowing across the junction will be equal to IN, which is this one here, and IP. Note that although electrons and holes flow in the opposite direction, the current of course is in the same direction because they carry opposite charge here. So I equal to IN plus IP. Both these currents, as I've indicated, because it's a PN junction, both these current components, they increase exponentially with voltage. This voltage here, V that I've applied here, IN, increases exponentially with voltage. IP also increases exponentially with voltage, both the current components. And of course, the sum also then increases exponentially. Now, I've also shown here, I'm assuming that the doping in N type is much larger than the doping in P type, which means that the electron current is stronger as compared to the hole current here. That's why I made the line, this line for electron thicker as compared to this particular line. So IN is much larger than IP. Electron current is much larger than IP here. So by controlling the ratio of the doping here, what I can control is that for every hole which is injected here, I may have 100 electrons which are injected here. So then my PN junction is 100 times efficient in injecting electrons as compared to holes here. So by simply controlling the doping, I can control how much electrons go here as compared to the holes that come over here. And as I said, in a bipolar transistor, if I think of this as an emitter and this as a base, this emitter is heavily doped. That's why I was showing you the doping, 10 to the power 19, and this may be 10 to the power 17, which means that the electron current may be 100 times stronger as compared to the hole current that you see. Okay, 100 times, you can make it even 200, 300 times stronger as compared to the hole current here. Okay, so that's the picture that I have for, let's say, emitter-based junction, simply. Okay. All right, so let's look at then what happens. So this is so now this is an emitter, N plus. This is a base here, P type, and note there's a depletion region also. I have forward biased it, so electron current is moving. Holes are also moving. Electrons are much more than the holes. Okay, I equal to IN plus IP. All right. I take another PN junction here. So till now, it's only a PN junction here. And I take another PN junction. And this PN junction, base, it's only a P. I'm only calling it base for a moment. So it's grounded. And collector is connected to positive bias, which means it's reverse biased. This junction is reverse biased here, which means that the current that would flow would be very small. And current would flow due to what? Some electrons in P-type, and there are very few electrons in P-type. Some electrons here move over to this side, and that's one source of current. And the other source of current is some holes here move over to the P side, and that's the source of current here. Very small current flows because it's a reverse bias junction. Also realize why is the current so low? Is because the number of electrons here is very low. Electrons can easily flow into the N side. That's not a problem. But the number of electrons is very low, and similarly, the number of holes is very low. So that's the reason why current across this junction is very small. Now, if by some means I could increase the number of electrons here, then obviously the current can be pretty high. So it's low only because the number of electrons in this region is low. Okay. All right. So so I have two separate PN junctions. One junction here and the other junction here. Now what I'm going to do is put them together. Bring them together here. Merge them. Okay. So the two that you see here have been merged. Now realize what will happen. Earlier this was the electron current. A lot of electrons are getting injected into P-type region here. And the whole current here, keep in mind the whole current would be maybe 100 times smaller. Okay. So now what would happen is these electrons which are injected, earlier what was happening to these electrons? They will come here and they will recombine with the holes, or what they will do is they'll flow into the contact. They have nowhere else to go. Now what happens is I've taken these two PN junctions and merged them together. These electrons that you see here, they come here. And this region is very thin. From here to here is very thin. So what happens is these electrons, they move along to the N side. Earlier, remember what was happening was they were going here. Now they don't go here. So what happens is these electrons that come over here, the total thickness of the base is maybe 1,000 angstrom. So what happens is these electrons simply go over to the other side here, because remember the current, as I said here, current from P to N was low only because number of electrons was low. Now what happens is all these electrons which are injected into P region, all these electrons can move over to the N side. So the electrons which are injected from N plus region, most of them, what happens is they go all over to the N side. Very few recombine. And in addition, I have these holes here. What other current do I have? I will have some small number of holes that are here coming over to this side, and I've neglected it because it's a reverse bias junction. So that's the picture of current for a bipolar transistor in which emitter-based junction is forward biased, that you see here, forward biased emitter-based junction, and collector-based junction. This is collector and this is base. Collector-based junction is reverse biased. This is the picture that we have. Electrons which are injected from emitter, they come to the base, and from the base they travel across and they go all the way to the collector. And the holes that are here, they go here and they're collected on the other side. There are very little holes coming from this side to this side, and we can neglect it as a first order approximation. Okay. Hmm? Width of the collector can be less, can be more, doesn't matter. Why? Yeah, but you see the electrons that are here, they come over to the collector side. Collector is anyway n-type. Collector is n-type. It's like a, after that it's like a resistor, and they get collected. That's all. The base is thin. See, what happens is, as you inject an electron into the base is full of holes. So what happens is the electrons will start recombining with holes. Right? And so I have to keep the base thin such that most of the electrons that are injected here, they reach the depletion edge. Here, this is the depletion region of the collector base junction. And remember, this is the depletion region. What is the direction of the electric field? It goes here. So the moment the electrons that you see here, they reach the depletion edge, there's an electric field which pulls them away, sweeps them into the n-type. Once the electron comes into the n-type, there are no holes for it to recombine. Then it's safe. And the electron simply gets collected at the contact here. So the critical region is the base region here. The electrons that are injected here, they can recombine entirely with the holes over here. They can recombine if the base thickness is large. But if the base thickness is small, then the electrons will pass over, cross the base, and reach the other end. And we get a current here. So if you're injecting 100 electrons, let's say here, say 100 electrons you're injecting here, one hole is being injected here, let's say, right? So the total current would be 100 plus 1 related to that. 100 plus 1 carriers are crossing this junction here. Now what happens is the base is thin. Out of those 100 electrons, maybe, one electron recombines. Even one is large, I would say, if you keep the base thin. Even one doesn't recombine, or one recombines here. So what happens is, out of 100 electrons injected here, 99 will reach here. So what is the collector current then? Collector current will be equal to 99 electrons. Emitter current will be equal to how many carriers? 101. And base current will be equal to, one hole goes here, and one electron was recombining with a hole, so another hole has to come and replenish the hole that recombined. So the base current would be equivalent to 2 holes, right? So you can see the current magnitude. A lot of current here of electrons, and almost all of them flow here. That's the key thing in a bipolar transistor here. All the currents flow here, and very few holes go over here, and very few holes recombine in this particular region. And then you have this kind of a behavior. All right, let's continue and see this here. So if I neglect that small number of carriers that recombine in the base, I can say currents that are injected as a first order approximation, current which is in electrons which are injected from N plus, all that they do is they go all the way and into the collector, electrons. Okay, and this is the whole current here. So if you want to simplify, if the emitter base junction is forward biased, collector base junction is reverse biased, what you're saying is two dominant current components are there. One is the red one here, electrons going all the way here, and then there is a smaller component here of holes. There are other currents, as I said, holes also flow from N to P, but they're negligible. It's a reverse bias junction, so you can neglect it. So that's the picture that you have here. Is it acting like a transistor? Do I see a transistor here? How do I test whether it's a transistor? What do I need? I want my collector current to be independent of collector base voltage, right? That's the output voltage, collector base voltage. Base is ground, so I want my collector current to be independent of collector voltage or insensitive to collector voltage. And I want my collector current to be very sensitive to emitter voltage. Do we see that? Because what is the collector current really equal to? These electrons. Where are these electrons coming from? They're coming from the emitter base junction. So if I change this voltage, how do you think this current will change? It changes exponentially because it's a PN junction. It will change exponentially. The number of electrons that are injected will change exponentially with this voltage, which means what? The number of electrons are very sensitive to the voltage that I apply at the emitter. Something changing exponentially means very sensitive. On the other hand, do you think this voltage will do anything to the electron here? This voltage here? Now, this current that flows across this particular junction that you see here, this current is what? It's flowing across a reverse bias junction. In reverse bias junction, is the current dependent on voltage? It doesn't depend on voltage, because what can the voltage do? If you ask yourself, we'll see what can this voltage do? It can increase the electric field, right? It can increase the electric field. Now, why does a small current flow across a reverse bias junction? The reason is that we have very few electrons here. So the bottleneck to current flow is not that I have small electric field here. That's not the bottleneck to current flow. Less current flows in a reverse bias junction because I have very few electrons here, right? And therefore, if I increase the electric field here, it doesn't do much to my current. Whatever electrons reach here, they anyway get collected here. Whether you apply 1 volt here, 2 volt here, 5 volt here, it doesn't really matter, because collection of electrons is easy. Electrons easily flow across the depletion region and reach the N side. So that's not an issue. The issue is how many electrons are there in the P region. That is what determines the current here. So we can see that whether I apply 2 volts or 5 volts or whatever, I will not find this current changing much to the first order approximation. So I have a current here that you see, which is independent, almost independent of collector voltage, doesn't change with collector voltage, and is very sensitive to emitter voltage here. So I'm seeing a transistor action here. So again, IC will be predominantly equal to IN. This is my IN here that you see. And emitter current that you see here, emitter current will be made up of IN plus IP here. These are the two components of emitter current. Collector current is simply equal to this here, IN. And base current will be equal to this current here that you see. Where base current that goes in, what does it do? It supplies holes. And where do the holes go? The holes go here. So the base current is simply equal to IP. This is IP here. So this is IP, this is IN. Emitter current is sum of these two. Collector current is simply this one. And the base current that you see here is IP here. Okay? And one can see here that if I talk about the ratio of base collector current and base current, IC by IB, IC by IB will be equal to IN by IP. IN is here, IP is here, and that is much larger than 1. And we call this as the current gain of the bipolar transistor. The base current is much smaller than the emitter current or the collector current here. And that's called the current gain of the transistor here. Okay, so far what I've done is I've drawn the bipolar transistor in this manner here. I've connected an emitter voltage here. I've put this as ground, and I've connected a collector voltage here. I can do the opposite, slightly different here. I can make emitter ground. I've connected a base voltage which is positive. Okay, let's say this is 0.7 and this is 5. And note what happens. Base emitter junction, all of you can see, is forward biased. Base is at 0.7. Emitter is at 0. So it's forward biased. Collector base junction. This is at 0.7. This is at 5. Obviously, this is reverse bias. So I can do this also. Same thing will happen even in this case. Note, because this is forward biased here, electrons will be injected. They'll travel all the way to the collector. Holes will be here. And I have the same operation as before. So whether I apply the voltage from this side, all I need to do is ensure, in this case, that emitter base junction is forward biased, collector base junction is reverse biased. Okay. So IC that you see here, as I said earlier, is basically equal to IN. And that current will go exponentially with base emitter voltage. Why? Because it's a PN junction diode. Base emitter is nothing but PN junction diode. The number of electrons that are injected, they change exponentially with base emitter voltage here. So IC, which is this current here, is IN, which is injected across this particular junction. That's simply exponent VBE by VT. The proportionality constant would be equal to some saturation current. Okay. So we can see here that the transistor that we are talking about, we said ideal transistor should look like this. Okay. What does our transistor look like? It doesn't look like this, but what it looks like is, let's see if this makes sense. Does it look like this here? Between base and emitter, what do I have? A diode. There's no issue here. Between base and emitter, there's a diode. Okay. And look at the direction of the diode from P to N. So we have drawn a diode here. What do I have between collector and emitter? Between collector and emitter, what do I see? What is flowing between collector and emitter? This current, right? This red arrow that you see here. And this current is what? IN. And IN goes as what? Exponent VB by VT. It depends primarily on the base emitter voltage. It's independent of collector voltage. So I've just shown that there is a current which flows here. It's a function of only base emitter voltage. I've not written exponential here, just written a function. So it's a function of base emitter voltage here. All right. So can we see a resemblance between the two? Right. There's a resemblance between the two here that you see here. Well, I don't have an open. I have a diode here. And in here, I don't have a GMVI. It's not linear, but I have dependent on input voltage here. And I have a almost an independence with respect to the output voltage here. So you can see this one here is resembling the ideal transistor that I have. Okay. Alternative representation. So this is one representation that I had here. Now note, I've denoted here that I have a current here because this current is this one here. This red one. This current is exponent of VB by VT. So I've denoted it by a voltage dependent current source. Voltage dependent current source. The only thing is it's a nonlinear voltage dependent current source here. Now can I also represent it by current dependent current source? Why? Because note, what is the current that is flowing here? This red one, right? IC is this one here. This current is, and what is the current that is flowing in the diode? It is this one. This is between base and emitter. It is this current only. Note, between base and emitter is this current, right? This is the current that is flowing here. Now, this is the base current here. This one is the base current here. And this is the collector current here. And what is the relationship between these two currents? IN and IP, what is the relationship? Beta. We said that this current, red current, electron current, is beta times larger than the whole current here. Right? Go back and see this relationship. We said that IC by IB. IC is this red one here. And IB is this current here. And the ratio is equal to beta. So can I now, based on that, write that this IC is nothing but beta times the current that flows here. And therefore we get this circuit here. Another way of representing the transistor is like this. So between base and emitter, I have a diode. So I have a diode here and this is the current IB. And between collector and emitter, I have this current. I can write it in terms of base emitter voltage, or I can also write it in terms of beta times IB here. And therefore, we have this representation of the transistor also. Sometimes this representation is used very commonly because often collector current is written in terms of the base current here. Okay. So note that IB that you see here is a PN junction diode current. So IB we can write it as some saturation current, exponent VB by VT minus 1. IC then will be equal to beta times IB. So beta times this one is written as some IS, exponent VB by VT. IC is also exponentially dependent on base emitter voltage, and IB and IC are related to through this quantity called beta, current gain. And F, you will see in a minute what F means. It means the forward action when currents are flowing from, when electrons are being injected from emitter to collector. So that's the forward mode of transistor operation. That's why the word F is here. So that's another model of a bipolar transistor that I have. In many of the circuits, for example, that you are given, wherever you see a bipolar transistor, you can substitute this particular model, a DC circuit especially, and you can calculate what would happen in the circuit. You can analyze the circuit based on this particular model. Okay? Yes? Between base and emitter? There are two currents. Which two currents? One is IB, another is IB. Another is? Okay, all right. Now note, when I denote between base and emitter, I'm talking about what is the terminal current. Terminal current. What current flows in this terminal and what current flows in this terminal here. So if you go back, this current doesn't flow into the base terminal. So that's why it's not a part of my base terminal here. What goes into my base terminal? So a current goes in, and you have to ask, what does this current do? This current supplies the holes which go over here. It's not linked with this current here. Okay? So that's why when I draw like this here, what flows is only the holes here from this side. In the emitter, you're right. In the emitter, I have both of them, this and this one. And so what happens is, in the emitter node, the other current that flows in is this one here. So emitter has both this. This is the hole current, this one here, and this is the electron current. So the hole current is coming from here, and the electron current is here, and the two add up, and you have both of them. So in the emitter terminal, you have both the currents. In the base, you have only the hole component, and in the collector, you have only the electron component. They all, okay? All right, so I'm showing the same things now. I represented transistor in one way. This is another very common representation of transistor. In terms of graphical picture, let's see if this makes sense. This is my base current here, and this is my base emitter voltage. Does it make sense that it has a characteristics like this here? Because base current is what? Hole current, and it changes exponentially with base emitter voltage here. So that's my base current versus base emitter voltage. Collector current versus base emitter voltage also looks like this. Why? Because collector current is electrons which are injected from here, and electron current also changes exponentially. So that also looks like this here. Collector current versus collector base voltage. It looks like this here. Because collector current node is electron current, electrons which are injected from here, they reach all the way here, and the collector current does not depend on the collector base voltage here. So I've denoted it by straight lines here. So this is the transistor that I get here. Transistor that I have is base current relationship with base emitter voltage, collector currents relationship with base emitter voltage, and collector currents relationship with collector base voltage. What is this characteristics that I will call? Collector current versus base emitter voltage I will call transfer characteristics, because it's output current versus input voltage here. So this transfer, and this is output characteristics here. Okay. This is the operation that we often call as a forward active mode. This operation where emitter based junction is forward biased, collector based junction is reverse biased. It has a name that we call this name for the operational mode as forward active mode. This is the most common mode. When I make amplifiers, I operate my transistor in the same manner here. Emitter based junction forward bias, collector based junction reverse bias. We call this as the forward active mode. This is how now actual transistor looks like here. So these are just mathematical representations. Look at this transistor here. This is IC versus VCE. IC versus VCE. Okay. Now note here, IC is here, and is being plotted versus VCE here. All right. That's how it is being plotted, and is being plotted for different values of base current here. IB1, IB2, IB3, and IB4. Now let me explain a little bit here. I said IC should be independent of VCB. That's what we said, right? That my collector current that flows here should be independent of the collector base voltage here. Because collector base voltage is what? The reverse bias voltage on the PN junction. Collector base voltage is the reverse bias voltage. Collector current should not depend much on the collector base voltage. That's what I have said. There's a difference between the collector base voltage and collector emitter voltage here. Collector emitter is between this region and this region here. It involves two junctions here, this junction and this junction here. All that I'm saying right now is collector current is independent of collector base voltage here. Now this is a plot of collector current versus collector emitter voltage. Okay, so it's a different plot. Now let's look at this particular plot here. VCE that you see here, I can write it as VCB. The voltage from collector to emitter is same as the voltage from collector to base plus the voltage from base to emitter. Okay, base to emitter. So VCB plus VBE here, and VCB I can write it as minus VBC. Okay, so far it's okay. If my base emitter junction is forward biased, I know my VBE is going to be 0.7. So I substitute here 0.7. So my VCE is 0.7 minus VBC. Okay. Now, when is my collector base junction reverse bias? Up to what point? I have plotted here VCE. My junction, collector base junction, can be considered reverse bias when VBC is what? Negative. Right? When VBC is negative, then I have reverse bias collector base junction. So when VBC is negative, VCE will be more than 0.7. What can I do to the reverse bias on collector base junction? At the most, I can bring it very close to 0. You know, maybe if I make it VBC equal to minus 0.05, you may say, well, it is still reverse bias, right? VBC is less than 0. So at the most, if I draw a line like this denotes the boundary. To the right of this particular line, what do I have? Collector base junction is, note, reverse biased. To the left of this particular line, collector base junction is now getting forward biased. Because to the left of this particular line, VBC is greater than 0. But all of you know that forward bias of a junction really means what? I have to apply, you know, maybe 0.5, 0.6 volt, then only it gets really forward bias. The effects of forward bias you begin to see. Okay. So ideally, collector base junction starts getting forward bias right from here. But until you make the collector base junction forward bias by a certain amount, you won't see its effect. Okay, so we'll come to that. So now note that this is the region which is the collector base junction is reverse bias. And this region is exactly like what I've drawn. I see, as I said, with VCB, it is straight. And that's what you see is straight here, not changing. It's only when the collector base junction becomes forward bias that you begin to see something else happening in the transistor, which we'll see why current begins to fall and all of that. We'll see in a minute here. Okay. So this is the characteristics IC versus VCE here. And realize that at this particular point, to the right of it, the collector base junction is reverse bias, and I have what I call as forward active mode. To the left of it, my collector base junction is getting increasingly forward bias, and I have a different mode of operation. So all I've explained so far, I've explained to you by saying that emitter base junction is forward bias, collector base junction is reverse bias. Okay, so that's the normal forward active mode here. So this is what we have in a transistor. Bipolar transistors operation is a little bit complex. You can divide the operation into 4 parts here. So you have 2 voltages, base emitter voltage and collector base voltage. You can have both these voltages which are positive, base emitter as base collector, both are positive. It means both the junctions are forward biased. When base emitter voltage is positive, it means base emitter junction is forward biased. When base collector voltage is positive, it means base collector junction is forward biased. So when both the junctions are forward biased, we call the transistor's operation, the mode of operation as saturation. When base emitter junction is forward biased, collector base junction is reverse biased, FNR that you see here, we call it forward active. This is the opposite of this one here, where base emitter junction is reverse biased, collector base junction is forward biased. So we call it the reverse active. Effectively what you're doing is you're using your collector as emitter and emitter as collector here. So we call this as the reverse active here. When both the junctions are reverse biased, base emitter junction is reverse biased, collector base junction is reverse biased. If all junctions are reverse biased, I'm not going to have much current in my device. This is a region which we call as cutoff. Very low current here. So I'm going to have current flowing in my transistor in all 3 regions here. Significant current will flow here, here, here. The only place where current doesn't flow is in the cutoff, or very low current flows is in the cutoff here. Okay, so these are the 4 modes in which the transistor works here. I have already explained to you how forward active works here. When emitter base junction is forward bias, collector base junction is reverse bias. We've already seen forward active. You can also understand reverse active. Reverse active is nothing but just simply the inverse of it. Use collector as so electrons will be injected from collector, they'll go all the way to the emitter. So it's just the inverse. So we already understand reverse active, because forward active and reverse active are the same. Cutoff is trivial, both junctions are reverse bias. The only thing we have to understand is saturation. what happens in saturation. Okay, so let's stop here and